third lecture, which will be the final lecture, so there will be changes in, so tomorrow, I'm finished today. So yesterday, so we talked a lot about this concept of information leakage, right? So we looked at systems that inherently leak information, either by design, because we want to leak some information, like the password changing example, or this example of statistics, like when you want to extract some statistics and make it public. So there's some leakage that is inherent in the system, or because the leakage is unintentional but unavoidable because of timing channels or power channels or things like that, right? So we saw some systems like that, and the motivation is that we want to try to quantify the leakage, right? And we saw that we do this using notions of information theory, so entropy notions. And what we do is we take these information theoretic channels as a model, have an input and an output, and we use, so the secret information is the input, the observable information is the output, and basically we use some entropy measure to measure how much uncertainty an adversary has to begin with, so before we run the system. Then we have a conditional entropy measure that tells us how uncertain the attacker is after the system, and then the difference between the two is what we call leakage, right? So leakage is how much uncertainty we lose because of the channel. And then there was a lot of discussion about this operational characterizations of this entropy notion, right? So just coming up with a formula doesn't say much. We need to have in mind what kind of attacker we are dealing with and what the entropy notion captures. And we saw two entropy notions, standard entropy and mean entropy. So the one corresponds to maybe not that natural attacker that tries to figure out the secret using these Boolean questions about whether the secret belongs to a set or not. And then the success of this adversary is the expected number of questions that he has to ask. And then we saw that maybe this is not that natural in some cases, because sometimes what we care is how likely it is for an adversary to guess a secret. So this led us to a simpler notion, the mean entropy leakage measure that captures exactly this. So what's the probability of guessing for an adversary to guess a secret, right? Okay. So, and of course I can continue doing this. So now I could, give you arguments about why mean entropy leakage is not that natural, all right? So yeah, I can give some argument about this. So mean entropy leakage assumes an operational scenario when the adversary benefits by guessing the secret exactly. So two key points here is exactly and in one try, right? So essentially the adversary only wins in this operational scenario if he manages to completely guess the secret, right? And he has one try to do that. And of course, you could easily imagine other scenarios. For instance, I mean, in practice, even if you can guess a secret partially or approximately, then maybe this is good enough for you, all right? So if the secret is a password, then you can guess part of it successfully, then maybe an adversary is already gained something out of that. Or maybe if the secret is my geographical location and the adversary cannot guess it accurately, but can guess it within a radius of a few meters, then it's okay. And of course, the adversary could also be allowed to make multiple guesses. So maybe an adversary has 3 guesses to perform, so three say, opportunities to perform his attack. So if he can guess a secret in 3 tries, then it's as good as one. Or maybe the adversary is penalized for making a wrong guess, right? So maybe if the adversary thinks that something is a secret, so he tries to break into your system, but he's wrong, and maybe this will trigger some alarm that will be he will be penalized for that, so it will make things worse. So yeah, and then of course I could maybe take each one of them and try to create some leakage measure that corresponds to some choice of an adversary that tries to partially within some epsilon guess a secret or has 5 tries or whatever. And of course, every time that I might do something like that, somebody could come back and say, okay, but this is not really the adversary that I'm interested in, right? So it's clear that no single leakage measure can be appropriate in these scenarios. So what I'm going to do in the continuation, I'm going to try to have a model that's sort of parametric on this operation scenario, right? So I'm going to have a concrete operation scenario, but I will have the flexibility to adapt it to my needs. So first thing. And the second thing, I will see what kind of results we can have that are robust with respect to all of these operation scenarios, right? Can we have bounds that say no matter what is my adversary, the leakage cannot do more than that? Or can I compare systems without specifying a specific operation scenario? Can I say that C system is always better than, system A is always better than B, no matter what is the scenario, no matter who is the adversary? Right, so is it, okay? Alright, so unfortunately I'm going to change a little bit the notation, so have a slide about that so just to make things clear. So the continuation, whenever I'm talking about the prior probability, I will call this pi. Okay, so pi always refers to prior. Secrets will be denoted by x, and by capital X, sometimes the random variable corresponding to the secret. Observations are y, and then W are guesses, so I'm going to explain what are these guesses, right? And then you can think of guesses either as secrets, so I'm trying to guess a secret, or maybe something different, right? So maybe what I'm trying to guess is not a secret. So I'm gonna explain what this means. All right. So this brings us to this framework of G leakage. Okay, G leakage will be this metric, leakage metric parameterized by something, and what will be parameterized by will be this notion of gain function, right? So the idea was to start from mean entropy, try to look what's the organizational scenario of mean entropy, but then introduce some parameters that allows some flexibility. So, okay, so this coming to the gain function. What's the operational scenario here? So the operational scenario is that there's a finite set of guesses that an adversary can make about the secret, right? So I have my secrets. In every execution, one of these secrets will be the real one, and then an adversary. So he might be interested about something, right? That maybe it's my exact secret, but maybe it's something different, some property of the secret, or some approximate value of the secret, or whatever. Okay. So an adversary can have like a set of guesses that can be whatever. It's up to me to decide that he can make about the secret. All right. So that's first parameter. So I need to come up with what a reasonable set of guesses this could be. And then for each guess W and value X, so when X is my real secret and W is the guess of the adversary, there is a gain given by this gain function that the adversary gets by choosing W, by making this guess when my actual value is X. Alright? So I have my secret, the adversary gets to make a guess, and this is his gain. Alright? So the gain function is basically a function that given a guess and the secret gives a value between 0 and 1. Right. Why 0, 1? Just to have range. Okay? So for instance, mean entropy leakage corresponds to this scenario, right? So a scenario where the other side makes a guess, in which the set of W, the set W is exactly a set of secrets, right? So in the mean entropy case, the adversary actually guesses a secret, so tries to figure out the secret. And then the gain function that we use is what we call the identity gain function. So the gain that's assigned to W when X is a secret is 1 if W is equal to the real secret and 0 otherwise. Right? So this is the simplest case that you can imagine. The guess is the real secret. If I guess correctly, I get 1. Otherwise, I get 0. Right? So, still okay so far?
What would be the gain of the Shannon?
Yeah, that's a good question. It's not as simple. So yeah, Shannon entropy to do it exactly in this way. I mean, you can do it. So and there is a result that I'm not going to discuss about this, but you could model any entropy function under mild conditions. But for Shannon, if you try to do it this way, it will be a gain function. So first of all, the set of, so you can do it, but the set of guesses needs to be infinite. And then the gain that you get for, so basically this guess will be a probability distribution, and the gain you get for that is the minus log with the probability distribution. So it's, the intuition about this is not that clear. I mean, you can do it, but yes, Shannon, you can do it like this, but it will not, you will not gain any good intuition because of that. All right. So now, okay, so this defines my operational scenario. Okay, so as before I started an operational scenario, with the only difference here is that the operational scenario is parameterized by these gain functions and the set of guesses. All right. So now the second thing to measure is what is how do I measure the success of the adversary? All right. So the adversary plays this game. So what I'm going to do? Well, very naturally, I'm just going to define the guess as I'm going to call prior vulnerability, right? Not entropy yet, vulnerability. So the vulnerability of a prior pi given a gain function g. So basically, I will assume that the reasonable attacker will make the choice that maximizes his gain, right? And essentially, the formula will the vulnerability will give the expected gain of the adversary in this game, right? So essentially, I need to maximize my number of guesses because I assume that the other side will make the best choice. Okay, and then for each guess, what I'm going to do here is that so when I'm going to make a guess, when I have fixed the guess W here, this gives you the expected gain of the adversary average overall possible savings, right? So this is the expected guess, the expected gain when I guess W, and I'm going to make the best guess so I maximize the product.
So the guesses are independent from each other?
So the guesses are independent from each other, yeah. So of course the guesses is completely arbitrary. So maybe there are sets that they have some semantic overlap, right? So maybe the guesses are, say, subsets of secrets that could overlap, right? So what I mean here that independent from each other is that I make one guess, right? So I will guess just one thing. In that sense, they're independent. But of course, they could be, so they could have structure, and this structure, I mean, maybe there is some semantic overlap.
But you could also remember what were the previous guesses.
I know, so I'm just going to make one guess, right? So if I need to make more guesses, then this needs to be encoded inside the guess, right? So maybe the guess is it's a sequence of things that I'm performing here. So I mean, I'm just going to consider this W as an opaque thing, but maybe it has structure inside, right? So yeah, the guess would be anything. All right. Okay, so vulnerability was included by the basis for my limit measure is the expected gain overall possible guesses, and it's maximum because I'm using the maximum. So for the posterior thing, what I'm going to do? Well, I'm going to do this trick of converting. So for each output y. By this, I mean the posterior distribution that I obtained using the usual base thing that we were doing yesterday, right? So for this y, I'm going to construct the posterior distribution, I'm going to measure the vulnerability of this, and I'm going to average overall outputs, right? So I was doing exactly the same thing for mean entropy. And for some entropy, it was similar, just it happened not in the level of vulnerability, but in the level of entropy. So it had the log inside. Right. And now, of course, the point here to make is that when I construct this posterior, so from the prior and y, the guess that will be, so inside this formula, the guess that will give the maximum gain might be different, right? So everything y, so this is exactly the whole point. That when I say y, maybe before a priori I was guessing some w1, but then when I see the particular y, this makes me change my mind and guess something else, right? And this is what causes the leakage. Right. And then the G-leakage is produced by first putting the log to convert this vulnerability thing into an entropy-like. So this vulnerability is like the lower it is, the better it is for us. So the worse for the attacker. So entropies work the other way. So we take the log to make it look like an uncertainty, and then we subtract the one from the other to measure leakage. All right. So the same thing we're doing before. So leakage is what remains from the uncertainty, essentially there is a minus log. So you can see this as a minus log. The prior entropy minus this, the posterior entropy. So what remains from my entropy after executing the channel? And then again, the G capacity. So sometimes I have a specific prior that I want to reason about. So I'm using linkage. Sometimes I don't. So I want to maximize things. So I'm taking the soup overall priors of the linkage. This I would call G capacity, right? The maximum linkage, maximize overall all priors, right? So essentially, it's more or less the same story. The key point here is changing the operational scenario and coming up with this formula as a natural way of measuring the effectiveness of an attacker in this operational scenario, right? Okay. Right. Good. Okay. So what? Of course, the question here, okay, this is nice, all right? So we have a more, say, flexible model, but what can you do with it, all right? Okay, we can do mean entropy linkage, but this we could do before. What else can we do? So the next thing is this gives us the flexibility to do lots of interesting things, all right? So we can model a situation where the adversary is interested in guessing a secret approximately, right? So maybe the secrets are geographical locations, right? Or anything that we have a metric to talk about the distance between secrets. Okay, so there's this notion that maybe this secret is close to that or not. And then the gain maybe is something like 1 minus this distance, or some function of this distance between secrets, right? So this would correspond to an adversary that, okay, if he guesses the exact secret, he's perfectly fine. But if he's a little bit wrong, okay, so it's not really a problem, right? He's equally happy, or maybe a little bit less happy, but still happy enough, right? Which is in sharp contrast with the mean entropy situation where any wrong guess is bad. Yeah, and also this leads us to some interesting situations in which the guess might not even be a secret. So you can imagine that a user might be in each one of these 4 locations, and then if you do the computation, it's a priori, right, before I have any knowledge of my system, if all of these locations have 1/4 probability, it's actually better for the adversary not to guess any of those locations, but to guess their sender. Because since he doesn't have enough information about it, if I make this location as a guess, then on average, I will be farther away from the real answer than if I guess the sender. Because I mean, the sender, I never guess correctly, but I never guess also too far away. While if I guess this, sometimes I will guess correctly, but sometimes I will be very far off, right? So, I mean, there are interesting situations like that. So the guess does not even necessarily need to be a secret. Maybe it's something that you know the user is never there, but it's good enough for you. So another possibility is maybe I don't care about guessing the secret, but I guess I want to guess a property of the secret, right? So a property is a set of the secret satisfying this property. So maybe I care about the gender of the sender of my anonymity protocols, right? So I want to figure out is he a male or a female? Okay, so in this case, the guess is a subset of the secrets. And of course, if if the actual secret happens to be in the set I chose, then I get gain 1. Otherwise, gain 0, right? So I'm happy if I just guess the property of the secret, not the actual secret. So guessing a part of a secret, similarly, so maybe the secrets are long numbers, but as long as I can guess the first digit, I'm happy. So again, we view that as a guess being the set of all secrets that have the same first 2 digits as the real one. Or another interesting situation is that guessing the secret in multiple tries can be actually encoded in the guess, right? So in this case, the guess is a set of multiple actual guesses, and if the secret is one of those guesses, then I get my gain. It's as good as if I guessed it in 1 try. Otherwise, I get no gain.
Should should this gain function be monotonic with respect to structure of guesses, whether there are and so on? Guesses that ask more or less, the gain should respect this order?
No, I'm not. I mean, yeah, of course, you could imagine that you might want to add some, but for none of the results that I care here. So I don't assume any order in any of those sets. So the guesses I consider them as just some set. Sometimes I would consider it as being finite, just this for simplicity. But then more interesting things can be done with an infinite set of guesses. But that's it. I don't assume any structure. So there's any no notion of monotonicity. Yeah, but you could imagine that maybe for some result that you're interested in, then maybe the gain will be monotonic with respect to some metric or something like that. Yeah, but not. I'm not going to use anything like this. All right. So okay. So already we saw different scenarios that can be modeled with guesses. Another interesting thing we can do in this framework is using gain functions to distinguish channels, right? Programs. So let's see this quite interesting example here. So I have two little programs, okay, very simple, that they work on a 64-bit integer variable, right? And I assume that this is uniformly distributed and so forth, for simplicity. So the first one, what it does, so it sets the output to be the input or this long string that has just three ones in the end. So essentially what it does, it leaks all but the last 3 bits of x. Okay, so it's going to tell you everything about x except the last 3 bits, because the last 3 bits will always be masked here, right? Here, y will be the same as x except from the last 3 bits. So I leak almost everything. While b, I do a bit of different thing here. So so I'm doing this modulate here, and then if it's 0, then I'm going to reveal everything. Otherwise, I'm going to reveal nothing. So essentially, 1/8 of the time, okay, I'm going to leak all of x. Okay, 1/8 of the time, I'm giving you everything. The rest of the time, I'm giving you nothing. So for some secrets, consider that some secrets I don't like them, so take them. Okay, but other secrets I'm not telling you anything. Right, so it's clear that both these systems leak, right? They leak a lot. But then the question is, which one is worse than the other, right? I mean, they both leak, but what do I prefer? Is this one worse? I mean, this leaks a lot of things every time, but still leaves some uncertainty remaining. This one sometimes is very bad, completely reveals everything, but then the rest of the time is. So what's going on here? Okay, you say, okay, no problem. I'm going to take my measures. I like mean entropy. So I'm going to do a computation. Then if you do this with mean entropy, you're going to figure out that these channels both have exactly the same leakage, which is 61 bits out of 64. All right. So in this case, it's kind of clear intuitively that 61 of the 64 are like literally revealed. Well, here is a bit less. I mean, it's not a direct correspondence to bits, but the mean entropy in both cases is the same. Okay. So this means that essentially, if I care about the mean entropy adversary, then I don't really care, because essentially, mean entropy adversary, he will be equally likely to guess these secrets before running this problem, right? Because I mean, here sometimes he will be able to guess it immediately, all right? So he will be very very happy. He will have probability 1 of guessing it, but then the other times he will have very small probability of guessing it. Okay, so on average, the two states will compensate with each other. While here, every single time there is some uncertainty left, so I still need to make a guess that will succeed with some probability. Okay? So then, okay, you might ask the question, okay, but this is, what if I change to Shannon or something else, right? And then the nice thing is that exactly using gain functions, I can create gain functions such that the one, A leaks more than B, but also vice versa. So I could create some evaporation scenario that makes A look better. So you might be tempted to say, okay, but in mean entropy is the same, but with this gain function, A is better. So maybe I always choose A, if it looks better, or maybe B looks better. But then I can also do the opposite thing. Okay. So essentially, these two are not comparable for all gain functions. How do we do that? So the first gain function here allows 8 tries. Alright? So in the first gain function, I just have 8 tries that I can make about my system. Alright? And then with a little bit of spinning, you will see that if I have 8 tries, so I make 8 guesses, and if the secret is in any one of these 8 guesses, then I gain 1, otherwise I gain 0. Alright? So now under this gain function, this channel essentially leaks everything. So has perfect leakage. Because every single time, no matter what is the outcome of this channel, within 8 guesses, because the only unknown thing are these last 3 bits, okay? So within 8 guesses, I don't know in advance what will these 8 guesses will be. I mean, they will depend on the outcome of the first 61 bits. But as soon as I have the 61 bits, then I can construct a set of 8 guesses by just taking the same 61 bits and varying just the last 3 of them. And with probability 1, the secret will be one of these 8 secrets. Okay. So this will be pretty bad. It will be very bad for this attacker. While the second channel is not that bad, because in the second channel, okay, one eighth of the time I know the outcome, so I can guess it, but the eight tries doesn't help me more. I mean, 1 try is enough. Okay, I mean, I could guess it even with 1 try. Having 8 does not make things better or anything. And then the remaining of the situation, I have so much uncertainty. So in the remaining of the situation, nothing is leaked. All right, so I still have for the 7/8 of the secret space, I know nothing. So there's so much uncertainty in there that having 8 tries, okay, it gives me a little bit, more, a little bit increase in probability, but it's not that much. All right, so if you do the computation, this will have very bad leakage. Everything is leaked right here. The leakage will be, just a little bit higher than it was with the main entropy case. Right? So you might say, okay, so this is worse, right? And I mean, kind of intuitively, you might be tempted to say that this is worse, because you say, okay, everything is leaked but 3 bits. So, I mean, this cannot be better than that, right? And now consider this other gain function. So this G tiger gain function that works the following way. So imagine that an adversary has 2 options. So he can either make a guess about the secret, right? Or pass. So say, I don't make any guess, right? So he can perform his attack, or maybe he can choose not to perform the attack. If he doesn't perform the attack, then he doesn't gain anything, but he doesn't lose anything either, right? If he performs the attack and he guesses correctly, he's happy. But if he performs the attack and then the secret is different and he's wrong, then there is this bit of, this door that opens, and then you fall into a bit of tigers, right? The other side, all right? Or you can imagine, like a pin. If you guess a pin and you know it, it's okay. But if you're wrong, then the card will block, and it will be actually worse for the other side, right? So if the other side tries to block the pin to guess a pin, if he's wrong, it's actually he's going to make things worse because he's going to lock the card. So how can we do this? Well, I can make the set of guesses to be the secrets plus some symbol here to mean don't guess, right? Another gain function. Well, if the gain function of this guess with any secret could be say 1/2 or something small, right? Meaning that I'm not getting the full guess, but it's not 0 anyway because I didn't fall into the pit of tiger. While the guess of a correct guess, the gain of correct guess is 1, and the gain of a wrong guess is 0. Right? It's clear this? I mean, it's also a bit natural. Like if you especially think the pin PIN example, or a password that locks after 3 tries or something like that, then it's natural to imagine that a wrong guess might be actually helpful for the other side. And now with this gain function, it's actually the opposite case. So what's going on here? So let's look at A first, all right? So a priori, so first, if I was this attacker, so a priori, what would I do? What would be the guess that I'm making? So I have these uniformly distributed integers, 64-bit integers. I need to make a guess. A wrong guess hurts, but I can choose to pass. And if I choose to pass, then I get a little bit of gain, right? So what do I do? What would be the best guess in this scenario? I mean, the best guess is the one that maximizes the gain, right? So if I have 64-bit integers, uniformly distributed, the probability of guessing correctly is extremely small, right? So if I really make a guess, then most of the time, with almost probability 1, I will be falling into the pit of tigers. So my gain will be close to 0. While if I choose to pass, then it's better, right? So this is saying that an adversary that doesn't know your PIN will not try to enter it. This is what that says. Okay, because he knows nothing, and if he tries, then he's just going to block it. It doesn't make sense for him to try. All right? This is a priori, okay? Now we run the system, and we get some information, all right? What's the information? Essentially, all the bits except the 3 last ones, okay? So now we know a lot more, okay? But still, there's uncertainty. There's still 1 out of 8. So if you do the computation, assuming that the guess of this bottom is 1/2, right? So if you do the computation, you will figure out that actually, even if you have all this information and you just have 1 try, you're still gonna choose not to make any guess. I mean, even with all this information, you don't have incentive to guess because essentially the penalty for a wrong guess is so high. Of course, it depends on the numbers, right? How you construct the numbers, but you construct them in a way that so if the penalty for a wrong guess is big enough, all right? So if you like behead the adversary for a wrong guess, since there is enough uncertainty here, he will say, okay, no, I'm still not going to try. And this means that this channel will actually be a no leakage channel. It will have 0 leakage. So remember yesterday, even in the minute case, we had situations where there was 0 leakage, even though the channel is not like a perfect privacy channel. Just because the way the operational scenario that I'm considering doesn't actually help. So the channel does not help the adversary at all. Yeah.
If the gain of not guessing is non-zero, then that means you have some leakage. With the leakage you measure depending on that G, then making no guess is still a leakage. If G of bottom is non-zero, then not making a guess is already a leakage.
So. Okay, so the leakage is, remember, the leakage is the difference between the gain that I'm getting a priori and the gain that I get a posteriori, right? So since I have this possibility of no guessing that gives me, say, gain 1/2, right? So even a priori, I have gain 1/2, right? This is the gain. So a 1/2 essentially means I don't fall into the pit of tigers, right? This is 1/2. I'm putting it in 1/2 to distinguish it from 0, that is the actual tigers, okay? So a priori, I have gain 1/2. A posteriori, I still have gain 1/2 because I'm always still gonna choose to pass. So always, right? So the difference of the two is 0 leakage. Not 0 gain, 0 leakage. Alright. Alright, so this channel doesn't help. So even though it leaks in some sense, right, there is correlation between the input and the output. For this gain function, it's not really a problem. Well, on the other hand, the second channel, although somehow it feels more safe because 7/8 of the time doesn't reveal anything. If you take this gain function, now 1/8 of the time, the adversary that a priori was choosing not to guess, now he learns completely the secret, right? So now he can make a guess without being afraid of the pit of tigers. So now every single observation in this 1/8 subset of the secrets will give the adversary enough information to change his guess, and because of that, we get more gain, so the leakage will be non-zero. It has more gain a posteriori than a priori. Right. So the interesting thing here is that you have two channels. They look different depending on your point of view and mentality. You might be tempted to say the one is better than the other, but there are situations, there are attackers that you cannot, maybe that's the adversary, that's not the adversary you care about, or hit, but a priori there's no reason to say why the one is better than the other. Right. We did this with the game. Right. So is clear, this example? So later we're going to examine exactly how we can be sure that the program, so how we can establish a comparison between two channels that guarantees that the one always leaks less than the other, no matter. So the guarantees that we cannot have situations like this. All right. So this is what robustness means, right? So in this framework, so it's expressive enough to have a variety of comparison scenarios, and we can play with the guesses, and we can set the numbers the way we want, and reason about different attackers. But then, of course, every time you do that, then you could worry about how robust is your conclusions about leakage, right? So essentially now I have a leakage measure that depends on two things. The prior, so this is the leakage, based on two things. It's a function of the prior and a function of the gain function, all right? So the prior models the prior knowledge of the adversary, and G models other things, what is valuable to the adversary, or what is precious to us, what we care about losing. The question is, if we're not confident about picking a specific prior and a gain function, so if I'm confident about a specific prior gain function, it's fine, okay, with my analysis. Otherwise, what can I do? So let's see some results here. So the first tool that we were using also before is capacity, right? So capacity is just the maximization of leakage overall priors. And this at least eliminates the assumption about the prior. So if I don't know, how likely it is for the user to choose password, then maybe I want to maximize overall bit. So I want to talk about capacity. And of course, sometimes I might also want to have a relationship between capacity of different leakage measures, right? So one result here that's quite useful is that mean capacity is actually an upper bound on channel capacity. So if I take a channel and I look at the maximum leakage, the maximum mean entropy leakage overall prior distribution, this will be an upper bound of the maximum channel capacity, so the maximum channel leakage among all distributions, right? And remember also from yesterday that this is also easy to compute. This is just, if you have a channel, you can easily compute it. So this says that if you can bound that, you compute this, and this is small, or if you can have a way to establish bounds on that, then this will give you bound on sound capacity. Then another even nicer theorem that looks a bit counterintuitive is that mean capacity is actually an upper bound on G capacity for every gain function, right? So no matter what gain function you're using, so mean capacity will be, so a channel cannot leak more for a gain function than it leaks for mean capacity, okay? Which sometimes it might look counterintuitive, because you might say, okay, but maybe this G vulnerability here talks about k tries, so it gives the adversary k tries. So if you have k tries, then it's better for the adversary, right? But the important thing is that this is about leakage. It's not about vulnerability. Okay, so by picking a G that gives a lot of tries to adversary, it might make things better for the adversary to begin with, okay, and also a posteriori. But the leakage, okay, which is what we care about here, will still be bound. So this is a nice result, because essentially it says, okay, if you can bound this you can be safe. And no matter what the scenario I might think of, the leakage will still be small. Right. So of course, yeah, this is what I was saying, that the solutions, it does affect the vulnerabilities, right? So this is about leakage. So the vulnerabilities, of course, are affected. They can be bigger. So this is a subtraction of two things, right? And this is a subtraction of two things. So each one of them could be bigger for a gain function, for a particular gain function, but the difference between the two cannot. Right? Is this clear? Right, but even more interesting than this, so far we're using these leakage measures, we're trying to come up with numbers, some semantics about these numbers. 3 more minutes? All right, so yeah, sometimes you use these leakage measures to really talk about numbers and probabilities and all that. But in my opinion, what is even more interesting is comparison of channels, right? So sometimes I have two programs or two systems, two analytic systems, or I have a system and an optimized version of the system. And what I want to establish is some ordering between the two. So I want to be sure that the second system does not leak more than the first. So I can that's safe to basically replace the one from the other. So you can think of it as a sort of refinement, right? So I'm going to refine my system with the separate system, but in doing that, I want to be sure that the new system does not leak more than the previous one, right? And of course, I could use any of these leakage measures to compare systems, but if I do it, then this will depend on the prior and the particular gain function used, all right? So the question is there a robust ordering? What can we say about robust? So is there an ordering that will guarantee that no matter what prior or what gain function I'm using, this will be safe, all right? And then also, in particular, I would like this order to be something that is a structural property of the channel. Right? That I can look at two channels, and without going into leakage measures, because the leakage measure will necessarily depend on these priors and all that. Right? So I want to establish something that just talks about the structure of the channels, and that I have some results that says that if I have this structural ordering of channels, then this will imply a leakage order, and vice versa. Right? And now, the good news for deterministic channels is that there's a simple ordering that is robust and has been here for a while. It's called the lattice of information. So how does this work? So this is the deterministic channels, right? So remember, deterministic channels are channels that for each input, the probability distribution is a singleton one, so there's just one output that is given, right? So the deterministic channels, you can think of them as a partitioning of the secret space, right? So the secrets in the same block, the same partition. So we put the secrets in the same partition if they map to the same output. Okay. So for instance, imagine a country channel that maps a person to the country of birth. Okay. So this channel, so it takes as an input a person, right? So now you have an analytic system where secrets are people that could send messages on a network, and then for some reason this channel outputs the country of birth of this guy. So essentially, this channel partitions the set of users, so the secret space, into the people that are born in France, USA, and so on. Okay, so the deterministic channel is always a partition. Secrets that map to the same observations belong to the same partition. And now the ordering will be simply partition refinement. So what's partition refinement? Is an ordering that says that the partitions of one channel are basically sub-partitions of the original channel. Okay, so you could imagine that there's a C-state channel that gives for each person, it gives you the country where they're born, unless there are also states within this country, in which case it will output the particular state, right? So for US here, it will not just output US, but will output the exact state.
Not for Brazil.
Sorry?
Not for Brazil.
Yeah, not for Brazil, because it takes time to make slots. Yeah. All right. So then this C state, you can also view it as a partition, all right? And then the partition will just fine, all right? So every partition will be completely contained in a partition of the original thing. Okay. So whenever this thing happens, we'll have this ordering, and so this means that C state refines C count, all right? It has finer partitions. Every partition here. So if you take, California. All the people there will be completely contained in the previous partition. All right, so that's a natural stop, and we 15 minutes. Yeah, 15 minutes. All right.
Yay.